Hello, Calc class. So in the last video we had started working on the integral test, and the integral test says that under some conditions, if a series converges if and only if the integral converges. So you can figure out if the integral is finite or infinite, and that tells you whether the series is finite or infinite. So we had just done the case where I proved that if the integral is infinite, so it diverges, so does the series. And I was moving on to the other direction, that if the integral converges, so does the series. So last time I built this comparison based on taking rectangles that lie above the curve. This time we're going to do the opposite. We're going to stick in the integers again. So 1, 2, 3, and ending up at n minus 1. And we're going to stick in the right n endpoint. So from 1 to 2, stick in the right n endpoint. This will be f of 2 then, which is also a sub 2. Stick in 3, you go up here. Sticking 3 into this function, you get f of 3. But that's also what we're calling a sub 3. Okay. And we're sticking right-hand endpoints in now, so when you get down to the last interval, stick in the right-hand endpoint, you make that rectangle. This time all the rectangles lie below the curve, so that the area under the curve is greater than or equal to the area of the rectangles. Okay. Now the first rectangle is 1 wide and a2 high. The next one is 1 wide, a3 high. The last one is 1 wide and a sub n high. So add up those rectangles together, you get an a2 plus an a3. Last one is a sub n. And the area under the curve is the integral from 1 to n. Okay. If I'm going to talk about the convergence of an integral, an improper integral, then I need the integral to go have an upper limit of infinity, not n. So, but I can just compare it because it's a positive function. So if you make the interval integration longer, you're just adding more terms on. Okay, so there's the comparison I wanted to get to. And just because it looks neater mathematically doesn't make any difference, but what I care about is this one, how it compares to this one. So just because it looks neater, I'm going to add the number a sub 1 on to both of these things. Mathematically, it wouldn't make any difference. It just makes it look nicer. A sub 1 is just a number. Add it on to something else, it's just going to be some other number if it was a number, and if it was infinity, add that number on, it's still infinity. So it doesn't do much except make the calculations look nice, because then this is the nth partial sum. And this, well, I haven't done this yet, so I haven't made an assumption yet. But now we're going to make the assumption that the integral converges because we already did the case where it diverges. So let's suppose integral converges. So that means it's finite. Okay. Then a sub 1 is just a number, and this is just some number. So this, put those two numbers together, you get some other number, which I'll just call m. So when we talked about sequences back in section 11.1, I said that there's one theorem that's the most important in this chapter. And it doesn't come up in your homework, but basically all the things that help us establish which series converge and diverge, and which is most of this chapter, is based on this theorem, which I'll remind you what it was back in 11.1. Bounded above increasing sequences always converge. Okay, well, this sequence is bounded above because it's less than or equal to these two numbers added together, which I'm calling big M. So it is bounded above, and it's increasing because every time you add a term on, you're adding a positive number on, so that makes it get bigger. So for example, what I'm saying is that the n plus first term is going to have the partial sum is going to be the first n terms plus the next one. But we supposed it was a positive term series, so if you leave this off, it's just going to make it smaller. And then that's the definition of an increasing sequence. And since bounded above increasing sequences always converge, that means that the limit as n goes to infinity of this series exists. And that means that this series converges. Okay, so now you won't have to worry about the proofs, but what it comes down to is if you want to know if a series converges, you can try the integral test. That's a theorem. And if the integral converges, so does the series. If the integral diverges, so does the series. So the reason we did this, or at least we said we did it, was so that we could handle a new and simple looking example, but we haven't done it yet. So let's take a look at that now. So for example, does this series converge? Now previously we talked about the fact that none of our other techniques will work. It's not telescoping. The term test of divergence won't work because the terms don't go to the terms don't go to a non. The terms don't go to zero. If the terms do go to zero. If the terms go to zero, then the term test of divergence doesn't tell you anything. And the other kind is not geometric. So we're going to go off to the integral test. And the integral test says if you meet certain conditions, then you can just do the integral. If the integral converges, so does this series. Integral diverges, so does the series. But you have to make sure that you meet the conditions. So one thing is your a sub n is 1 over n. That's a positive term series. So that's one of the conditions. And your function that you make up just so it agrees with this has to be positive, continuous, and decreasing from 1 and up. Okay? Well, let's start working on those things, those three things. So, first of all, it's positive if your x is bigger than 0. Because the 1 is already positive, you just need the bottom to be positive. Okay? And then, where is it not continuous? It's not continuous at 0 because it doesn't exist. So f is continuous for x bigger than 0. Okay, it's also continuous for x less than 0, but I only need it from 1 and up, so there's no reason for me to go backwards and get the negative values, although it's true that it is continuous for the negative values. Okay, and then there's the decreasing part. Well, this is 1 over x, so when the x gets bigger, 1 over x gets smaller. And again, we're going to stay away from 0 because it doesn't exist at 0, and negative numbers, because we have to throw the negative numbers out already anyway. And it is true if the x gets bigger, 1 over x gets smaller for x greater than 0. That's the definition of what it means to be decreasing. So f is decreasing. So it is true that it's positive, continuous, and decreasing for x bigger than or equal to 1, because that would be a subset of x being greater than 0. But it's important to work that out. So f of x, which is 1 over x, is continuous, positive, and decreasing for x greater than 0. X greater than 0, that would include x greater than or equal to 1, which includes x greater than or equal to 1. So we can now apply the integral test. You have to show you meet the conditions of the integral test, or what you've done is not a useful calculation. You can check the integral first if you want to, and then go back and verify it, or you can verify before you do the integral, but either way, your conclusion doesn't mean anything unless you verify that you have met the conditions, namely these three conditions. Okay, so now let's do the integral. So that would be the limit as t goes to infinity of the integral from 1 to t of the function is actually just 1 over x. Okay. Antiderivative of 1 over x is the natural log of x. All right, and then you stick it in limits of integration. And minus the natural log of 1, but the natural log of 1 is 0, and log goes to infinity when you go to infinity. So the integral diverges. And that implies the series diverges. All right, see you in the next video.